Hi, everyone. This is part 2 of lecture 5. So in this part, we'll try to put some of the tools we just developed to use. Okay. So we looked at, composition and post-processing, and we'll see how those could be used to come up with a differentially private version of a popular clustering algorithm called Lloyd's algorithm. So in Lloyd's algorithm, I've got the input is a data set consisting of n points, and each of these points is a vector of real numbers. So for simplicity, we'll imagine that they're pairs of real numbers, although in general it works with d-dimensional vectors. And there's also a number k, okay, an integer k. And our goal is to find a set of k points, we'll call them centers, in R2, in the plane, that minimize the following cost. Okay, they minimize what's called the k-means cost. K-means cost, which is the following thing. So I'm going to sum up over points in my data set the distance between xi and the nearest of my cluster centers. So I'll call the centers C1 through CK. And for so what's going to happen here, CJI is the closest center to xi. Okay, so for example, suppose my data looks something like this. I've got some clouds of points. All right, and we're in the case k equals 3. And now let's say I've got suppose my centers were the following. Let's say I had one over here, one over here, and one over here. Okay. So then what I would do is I would say for each one, for each data point, I'm going to look at the distance to the nearest center. So let's say for this data point here, the nearest center might be that one. And so I would look at that distance and I would square it, and that would be its contribution to the cost. But for this data point here, its nearest center is this red X, and so its contribution to the cost would be this. So for each data point, I'm gonna find the closest center, look at the distance to that center, square it, and that's that point's contribution to the overall cost. Okay, so if all of my points are close to some center, then my cost will be very small, and if some of my points are very far from a center, then those points will contribute a lot to the cost. It'll raise the cost. So what I'm trying to do is find like a set of centers that's kind of simultaneously as close as possible to lots of the data points. All right. So if k is equal to 1, like if I'm just trying to find one center, the best choice is just the mean of the data set. So the optimal solution, let's say C1, is just 1 over n times the sum of the data vectors. It's the average of the data vectors. But for k greater or equal to 2, it's more complicated, and in fact, in general it's NP hard to solve exactly. Though there are very good approximation algorithms. Unfortunately, most of the approximation algorithms that have really good approximation guarantees are complicated, and in practice, people tend to use a set of heuristics, one of which is called Lloyd's algorithm, and that's what I'll describe. Okay, so here's my algorithm. The way it's going to work is so this algorithm is not it doesn't have I'll describe it, doesn't have like a really good approximation guarantee, but it tends to work well in practice, and even though in the worst case it can perform poorly. We're not really going to worry about how good an approximation algorithm it is. What we're going to try and find is a differentially private algorithm that mimics the basic algorithm, the original algorithm. So here's our algorithm. What we'll do is we'll start with some centers that are, we'll call them the centers with superscript 0. They'll be random in the, they'll just be randomly generated, randomly initialized. Often in practice, they'll be generated by picking points from the data set. But that's not how we're going to do it. Just imagine they're sort of chosen from some initial distribution. And now what we're going to do is we'll proceed in stages. So for t equals 1 up to some number t, which is a number of phases that is given to us. We'll so think of it as a fixed quantity. And now we'll do the following thing for each j. So the first thing we'll do is we'll figure out currently which are the data points that are closest to cluster center j. Okay, so we'll look at the set of I such that cluster center of the current cluster center, so that's from stage t minus 1. Cluster center j is the closest current center, center to data point xi. Okay, so what the picture you should have in mind is the following: is that these red points, they divide space into three regions according to, there are the points that are closest to here. I think this is roughly what it'll look like. So these are the points that are closest to this cluster center here. So this region, we'll call it like S1 if this is cluster center C1. This region here will be S2 for cluster center C2. And this region here, if this cluster center is S3, this region here is S3. So these are, S3 is all the data points that lie in this, what's called a Voronoi cell, this region of things closest to C3. S2 are the collection of data points that lie closest to C2, and S1 is the collection of data points that lie closest to C1. Okay. And then so based on these S's, what we're gonna do is we're gonna update our centers. We're gonna compute new centers. And the way we do that is we're gonna compute the new center C1 prime, say, to be the average of the points in S1. So we're just going to find the best single center, but for the points in S1. So that would look something like this in this example. In this, for S2, it would look something, the new center would be C2 prime. And for S3, the new center would be somewhere over here, C3 prime. Or maybe more like, over here, C3 prime. Okay, so that's the picture you should have in mind, and maybe we'll bring the picture closer to the code. Oops. All right, so that's the picture you should have in mind. We lost the colors, but that's okay. All right, so so now this is what we're going to do. We're going to compute new cluster centers. So we're going to compute averages, and so one way to write that is I'll take the nj will be the number of points in Sj, and then aj will be the sum of the points in Sj. And then my new cluster center is so Cj of t now for the tth time step is just the ratio of these things. So aj is a vector, nj is a number. We can divide them, and or we can write it. Maybe it's more intuitive to write it as 1 over nj times aj. Okay, so aj here is a vector. So are the x's. Okay, so this is the algorithm. And then when we're all done with this, we just return the final cluster centers. So C1 of T up to K of T. Okay. Now, there are various variations on this algorithm that people use in practice, and we're just not going to worry about those for now. Okay. What we're really after is a differentially private version of the algorithm. And so let's see how we can do that. So let's come up with a differentially private version of this algorithm. In order to do that, let's see, we're going to need a few changes. So first of all, we're going to make an assumption on our input, which is that we're going to assume that the x's have the property that they're bounded vectors. Okay, and we'll see why that's important. Okay. So this property you can enforce just by normalizing vectors. If a vector is too long, it can be shortened to have a certain L1 norm. We'll say 1 for simplicity. So notice that you might want to know something enough about your data to know kind of what ball to condense it to, but we'll just ignore that for now. So let's assume that we know, or that we enforce, that the xi's have norm at most 1. Okay, and now what we're going to do is we're going to we're going to add noise to each of our, at each stage of the algorithm, to these two quantities right here, 2 and 3. So the way we're going to do this is we're going to say, I'm going to, because these are sums, I can use the Laplace mechanism. I'm going to add noise to nj as follows. I'll release a quantity nj hat, which is nj plus noise, call it Z naught. This is, I'm doing this fresh for each T. So I don't want to overload us with subscripts, but there's like a different T for each. We're generating different noise at each stage of the algorithm. So here, Z naught is Laplace 2 over epsilon prime. And what is epsilon prime? Epsilon prime is the amount of privacy budget I'm spending at this step. So I'm going to define that to be epsilon over 2t. And then I'll say aj hat. Similarly, I will add noise to that, which is a vector. And these zi's will have the same distribution, Laplace noise 2 over epsilon prime independently and identically. Okay, and again, this is fresh noise at each step. I'm not reusing noise from step to step. Okay, and now my my new cluster center is just the sort of a pseudo average where I'm taking a noisy set of clusters, I'm a noisy sum, and I'm dividing by a noisy count. Okay, and you need some logic for the case where nj hat is negative, which can happen. Basically, in that case, what you should do is just throw out the current cluster center, just generate a new random cluster center for this cluster. Okay, but ideally, that case just won't come up. But of course, for the algorithm to be well defined, you do have to discuss it. So this is if it's like negative. Okay, and then again, you return the final set of cluster centers, or actually what tends to work better in practice is to return the average over a few, the last few iterations of the algorithm, but we're not going to worry about that. Okay, so this is our algorithm. Again, we're adding noise to at two intermediate points in the algorithm. We're adding noise to the counts of the number of points in each cluster, and we're adding noise to the sum. Okay. So why is this a reasonable thing to do? So let's just make some key observations here. If I define a function at each stage, I can define a function f1, and the function f1 is the vector of counts for these regions, right? Remember, there were 3 in this case for k equals 3 regions. In general, there are k regions. And this is actually a histogram, right? Once I've fixed the cluster centers from the previous stage, This this is a histogram, so it has global sensitivity GSF1 less than or equal to 2, at least when once we've fixed and output the cluster centers from the previous stage, C1 of t minus 1 up to CK of t minus 1. Okay. And similarly, we can talk about F2 of x. And F2 of x is just like the concatenation of the sums, the AJs. And I claim that that the global sensitivity of F2 is also at most 2 in the L1 norm. Okay, and that's because changing an xi, once I fixed the previous cluster centers, changing an xi moves, subtracts one term from one bin and adds another term to a different bin. Okay. And so the net change, consists of the addition or subtraction of 2 vectors, each of length 1, at most 1. Okay, their length in the L1 norm is at most 1. Okay, so that's a really important observation. So the fact is that even once I fix the cluster centers, the computation I'm doing is actually very low sensitivity. And so what I can do is add noise to that step. All right, so here is our algorithm, and now we're ready to prove the main thing we want, which is that this algorithm, this noisy Lloyd's algorithm, is epsilon differentially private. Okay. So to prove this, what we're going to do is we're going to imagine that we're releasing not just the final, not just the final clusters, but all the intermediate cluster centers. Okay. So our initial cluster centers, the ones with the 0 index, C1 to CK 0, they were initialized randomly. They don't depend on the data. So there's no privacy cost to releasing those. Okay. And then for the other stages, if I'm given C1 of t minus 1 to CK of t minus 1, we can view the noise addition, the teeth stage. We can view stage T, that is the teeth iteration through like this for loop over here. We can view the stage T as an execution of two executions of the Laplace mechanism. And the cost of each one, okay, so with a privacy parameter, epsilon prime, which is epsilon over 2t. Okay, so let's go up and see what's going on. So again, what we did is we added noise 2 over epsilon prime. So notice that our global sensitivity was 2. So that means that the cost to privacy, this is like running the Laplace mechanism with privacy parameter epsilon prime. And same thing for the second step. Okay. So again, we're using our sensitivity analysis to bound how much privacy we're losing at each stage of the algorithm. So each stage costs us epsilon over 2t. And as a result, the total cost, each stage costs us epsilon over 2t twice. Okay, so the cost per stage is epsilon over t. And then the cost for the total algorithm, cost for the whole algorithm, that's the sum over the stages of the cost at each stage. Okay, so that's t times epsilon over t, which is epsilon. Okay, QED. So what have we done? We've taken this popular heuristic and we've come up with a differentially private version which adds noise at the intermediate stages of the computation. And that's really useful because it turns out like many of the data analysis algorithms we want to use consist of like a number of iterations where each iteration is very simple. Okay, so and the same things that the reason we do that normally is for speed. The reason we aim for simplicity is because it leads to a more efficient implementation. But that simplicity has a big benefit in terms of reasoning about privacy. In the notes, there are some diagrams that show you like an execution of the algorithm on a specific inputs and on a specific input and sort of how it plays out. And you can look at that on your own. What I've done is I have implemented both the original algorithm and a noisy version of it in this Python notebook that I'm showing on screen now. I won't go over the code. I'll just say that it's it's pretty simple. The only place where we're doing anything tricky is we're just using or adding Laplace noise to counts and sums. I have to confess, I use the default Python random number generator here, which is actually not very secure. So this is definitely not production quality code, but at least it's enough for you to understand the general gist of the algorithm. And I'll just show you some pictures. So what is going on here? The red crosses are these are the initial centers for both the private and the non-private algorithm. And then the points have been clustered according to their proximity to to which of the red crosses they're closest to. So these are the regions, the S1, S2, and S3. Those regions are in this they're depicted by the colors of the points. Okay, so when we execute the algorithm, t equals 1, t equals 2, t equals 3, etc. What's going on is the red crosses show the positions of the centers that the non-private algorithm, the original algorithm, would compute, whereas the blue crosses show the noisy positions, what you would get from the noisy version of the algorithm. And what you see is that the red crosses converge pretty quickly. They're pretty stable after maybe the second or third iteration. And the blue crosses sort of take a little longer to stabilize. So as they go through iterations, they're drifting a little further away from the red crosses, but they kind of eventually, they converge to the same point after a couple of iterations. Okay, and as I mentioned in practice, what actually works very well usually is to average over a few iterations at the end. So that's actually what you see here in the very bottom plot. So because of post-processing, it's differentially privately, it's okay to release from the privacy point of view, it's okay to release all the intermediate cluster centers. So in particular, your final estimate can be any function of all those intermediate cluster centers. And the one that tends to work well is to take the average over the last few iterations of the cluster centers. And that's what I've shown here. And in this particular example, this is with about 2,000 data points and epsilon set to 0.5. So pretty stringent privacy parameter, and you get pretty good clustering of the data, pretty much identical to what you'd get non-private. Okay.